to have Dr. Garcia presenting for us. Arielly Garcia is an animal scientist with a master's and a PhD in animal breeding and genetics from the Federal University of Viçosa in Brazil. She is currently a postdoctoral research associate at the University of Georgia. Her research focuses on quantitative and genomic analysis in livestock breeding programs with a focus in cattle and swine. Her work includes population structure analysis using genomic data, pedigree reconstruction, genetic parameter estimation, genome-wide association studies, and the integration of phenomic and genomic information to support selection decisions. So I will turn it over now, Dr. Garcia, and we can get started.
Okay, thank you. Good afternoon, everyone. Thank you, Julia, for the introduction, and thank you all for joining us throughout my presentation today. I believe that most of the audience today doesn't know me, so I think it's fair for me to give a brief introduction about myself. My name is Arielly. I'm originally from Brazil, more specifically from a small city in Bahia state, northeast region of Brazil. In Bahia, I did my undergrad in animal science. The university where I studied was not very strong in animal breeding genetics. So for much of my undergrad studies, I worked with ingestive behavior of goats and sheep and rheumatological analysis of feed. In 2019, I moved to Minas Gerais, where I completed my master's and recently my PhD degrees at Federal University of Viçosa. And during my master's degree, I worked with data from dairy cattle, with G breed. This breed that I showed the photo here is a Bos Indicus breed, really common in Brazil. You can use like as pure breed or crossed with Holstein, what is really common, what we call Girolando breed. And during my master's degree, I worked with pedigree reconstruction. And the main objective with this was to develop a SNP panel for parentage test and assignment for this breed, because I don't know if you guys know, but the International Society for Animal Genetics already developed SNP panel for parentage test, but most of the SNPs are polymorphs only for like Bos taurus breeds. Also, the SNP sheep, the most of the SNPs are more polymorphic for Bos taurus breed. Only half of the SNPs considered in the high density panel, for example, are polymorphic for Indicus. We also studied the population structure, where we did runs of homozygosity, analysis for runs of homozygosity, and the diagonal of the matrix to assess the inbreeding of this population, and study the size, the effective size of the population. So during my PhD, my first project is still focused on G cattle, where I analyzed milk quality traits. The purpose of this project was more practical, and the results are being used on 2 farms in Minas Gerais. And I used the multi-trait model that considered protein and fat percentage, as well as somatic cell counting at the same model. So we could select the animals for quality and also the health traits at the same time, the health trait at the same time. So in 2023, I came to the University of Georgia at the invitation of Professor Daniela. As a research visitor, I worked on 2 projects here. The first one was the Beef and Dairy project, which brought me here today, and I will talk more about it later. And the second one was with swine, where I did a 3-month internship in the Netherlands and worked with a syndrome considered kind of new. It was first described in 2019 for a group in Germany. So, okay, here. And currently I'm a postdoc researcher here at UGA, and I continue to work with swine. But now with data from Pig Improvement Company, PIC, here in the US. I'm investigating the boar longevity. But returning to today's presentation, I had the honor of being invited to speak to you about my beef and dairy project. And if you have any questions or are curious about any specific point, please feel free to ask during or after the presentation, whichever you prefer. We call beef on dairy the product of crossing dairy cows with beef bulls. This practice is not new, but it has become increasingly common due to several factors. This includes heterosis and complementarity when cross different breeds, but also due to growing use of sex semen, because this allows farmers to select replacement heifers and inseminate them with sex semen, while the remaining cows are inseminated with semen from beef bulls. This strategy allows for the sale of surplus calves at a higher price because they are in general heavier and will later have a better carcass conformation, and it helps to handle fluctuations in the milk prices over time. Be honest, I was a bit surprised when I saw for the first time that in the US, beef and dairy herds represent around 22% of the beef production, because for me it was kind of high. But the problem is that some studies have shown that dystocia rates increase in dairy cows mated with certain breeds of beef sires, especially in breeds where the birth weight is high. But I would say that the main motivation of this project was the lack of information. Is easy to find studies comparing breeds, but most of them did not consider the genetic effect. So the lack of information was one of the big motivations. And as I just mentioned, some studies have shown that dystocia rates increase in beef and dairy scenario. And to help us measure the degree of difficulty of births, we have a well-known trait called calving ease, where calving ease is measured through scores. And here begins a new challenge, because everyone knows that scores are subjective. If you ask two people with different level of experience about the same birth, it's likely they will classify it differently. To help standardize this classification, we have predetermined and widely used scores. And I've included some examples here. First, I brought the scores proposed by the National Association of Animal Breeders. That score system was proposed by Berger in 1994, and it ranges from 1 to 5, where 1 is no problem during the birth, and 5, the extreme difficult. But also, the Beef Improvement Federation recommend for beef cattle, they use this score system. Also range from 1 to 5, but range from no assistance, or it means no problem, and 5 is abnormal. Actually, it is abnormal in most of the cases. For genetic evaluations, they don't consider this category because it's not inherited. So most of the cases, they consider from 1 to 4. But if you read European studies, you see they use most of the time scores range from 1 to 4. And in this case, is the inverse scoring, because 1 in this case is the most difficult birth, and 4 is the normal. Furthermore, so here you can see that in addition of the subjective to decide about the score itself, there is still a lack of a universal standard for classifying births in cattle. Furthermore, difference in easy calves rates is expected according to the cow's age, because we already know that heifers can have, we expect, more difficult calvings than cows, for example. And some authors have reported these results in beef and dairy, regardless of the side breed used in the crossing. So to investigate the genetic background of calving ease on beef and dairy, we wanted to know how heritable this trait is. So we estimate the variance components and genetic parameters for this trait. Also, because calving is a categorical trait, we wanted to know, to understand how to model it properly. And then we applied linear and threshold models. Additionally, we investigate which scoring system fits better in the beef and dairy scenario, given that beef and dairy use different systems for scores. And finally, investigate change if we consider only heifers, animals in the first lactation, or the first three lactations, where we have heifers and cows. For this, I received data from Peak Genetics, is a company from Euros Group, where we have Holstein and Jersey cows inseminated with Angus, Charolais, and Simmental bulls. Here you can see that the pedigree structure for the first three lactations, and this third generation here are my phenotyped animals. Square means males, circle females, and diamond shape is when we don't know the sex of the animals. And later, these animals were not considered in the analysis. Then we have dairy side and beef side. Here, it is a particular aspect of beef and dairy. In your case, the data came from farms, not from associations, which result in a shallow pedigree. And yes, UGA also works with associations, but no, we cannot cross information between companies. So because of this, we had here a very shallow pedigree, and the animals are not connected, because if you see, the beef and dairy side are not connected. The only generations that connect the animals are the F1s, where you have the crossed animals. I don't have any information above this or below this. Another point is that the pedigree in beef and dairy, because they don't have a common ancestor in this pedigree, we have two completely different populations. And these crosses in the US used to stop in the F1 generation, where the crossed animals are the final product. In addition, we have a lot of misinformation inside each population, because if you look of the dairy side, all the cows have information about the sides, but they don't have information about the dams. And for the beef side, only 400 bulls have information for at least one parent node. And because of this, it makes it impossible to detect inbreeding in this population. So the inbreeding here is 0. And we have many underestimated relationships, because if you think about the dairy side, for example, we have here cows that can be full sibs, but we consider just half sibs because we don't have information about the dams. So we consider calving is as a binary trait, where 1 was is and 2 difficult. And here you might be wondering why I showed all those scores in the motivation if I used the binary code, right? So, and to answer this, it's actually very common to group the scores for calving is, because some categories have a very low prevalence. We will see better when I show the prevalence of each score for each lactation, but please remember that one of my objectives was to investigate the combination of the scores, to combine these in a binary code. So what I initially received were the scores proposed by Berger in 1994, since the animals were born in a dairy system, and this is the most common scores used in dairy cattle. We have already seen the 5 categories before, and what I did was group them in 2 ways. The first, more similar to what's done with beef cattle, as the Angus Association does, for example, where 1 is considered easy and 2 plus, 2, 3, 4, and 5, it's considered difficult. And second, I use the definition used by CDCB, where 1, 2, and 3 is considered easy, calves, and 4 and 5 difficult. Here are the prevalence of each score from 1 to 5 for each lactation. Each lactation in this case is the colors. So we can see that the prevalence are quite similar. Almost 9% of the births were without any problem, regardless of the lactation order. And score 4 and 5 represents around 1-2% of this data. The difference in the bar size here is only due to the number of observations in each lactation. And here is another particularity about the beef and dairy that I want to draw your attention to. The number of records in the first lactation is less than half when you compare with the second and the third lactation. This is because, as I said, it is already known that the parity order can affect the calves. So farmers prefer to inseminate older cows with semen from beef bulls. And it can also be because cows that is not producing a good milk offspring in the first lactation were chosen to become, for example, a dam of a beef and dairy calf. And what about the prevalence when considering binary trait? Remember that I grouped this in two ways, right? Here I call like the beef cattle cold or cold 1 when I have easy calves as score 1 and 2+ as difficult. So we have all the breed combinations here. So Holstein and Jersey crossed with Angus, Charolais, and Simmental. And outside of the parentheses are the prevalence for the first lactation and inside of the parentheses for the first 3 lactations. So in the last row, we have the average. So the average here is representative, where we have 85% of the calves were easy for the first lactation and 88% for the first 3 lactations. Well, it is representative except for Holstein when we cross this with Charolais and Jersey when we cross this with Simmental, where we had more difficult births in the first lactation if compared with the other combinations. And these are the prevalence considering the grouping used by the CDCB. In this scenario, you can see that almost 100% of the calves were classified as easy. It means they received score 1, 2, or 3. So it leaves us with a trait with almost no phenotypic variance to be investigated. So here I spoiler that the analysis using this combination of score didn't reach convergence. And that's why you not see any results related of this combination in the future slides. So one of our objectives was already answered because I tried to test these 2 combinations of scores that I called code 1, code 2, and we already saw that code 2 didn't work in beef and dairy system in this data, this case. So the results, again, all the results that you see are only about this combination here, where we have 1 as easy and 2+ as difficult. And another objective was to compare linear and threshold model. This is because calving is a categorical trait, and in theory, we know that a binary trait, as is the case here, violates the assumption that we have a normal distribution of the residuals. In this case, what we expected is a binomial distribution. So because of this, the threshold model is the most recommended here in this case. Because we assume that a categorical trait has an underlying continuous inheritance with a threshold what imposes the discontinuity of this expression. The underlying continuous variable is what we call liability. So in a simple term, what we have in the threshold model is a transformation of categorical phenotypes into liability, what is continuous, resulting in breeding values on liability scale. And because liability has no biological meaning, it's common to transform breeding values into probabilities. Therefore, what we usually see is the probability of an animal having an easy or difficult calving. However, despite this, linear models are simpler, and some studies have already shown that linear models rank the animals in the same way. Therefore, regardless of the model, we would be selecting the same animals, and that's why we are comparing these two models. And we compared these two models in terms of computing time, rank correlation between the breeding values of the threshold and linear models, and we also validate the model's prediction using the linear regression method proposed by Legara and Riveter in 2018. And in this case, we have whole and partial data sets for the first three lactations. So in the first lactation, we omitted the phenotype of 11,000 animals. And in the first three lactations, we omitted the phenotype of 70,000 animals, right, around of this. So the analysis, the animals used for validation were born in 2022 and early in 2023. Then we performed a linear regression with DVVs from the whole and partial data set only for those animals whose phenotype we had omitted. For estimating the variance components and genetic parameters and predict the breeding values, we used this model. Here in the linear model, the phenotype is the score itself, while in the threshold model, the phenotype is the liability. The effects are the same in both models, and in black we can see the fixed effects of calf sex, dam and side breed combination, year season, and cow age is covariate. The random effects include the herd year, the direct maternal genetic effects, and the residual. These here are the assumptions for the model, and I just want to draw your attention to the covariance between the direct and maternal genetic effects. Initially, we considered these to be different from zero, but the analysis showed that in our data set, this covariance was actually equal to zero. So we consider the direct and maternal genetic effects as unrelated in this case, and we use the Gibbs F90 plus to estimate the variance components. After estimating these variance components, we fix these values in the system of equation and solve the system of equations using BLUP IOD and CBLUP IOD to calculate the breeding values for linear and threshold model respectively. Regarding the genetic parameters, we have the direct and maternal heritability for the linear and threshold models considering the first three lactations. In general, the heritabilities were low, ranged from 1 to 3% for the direct effect, whereas the heritability used the threshold model were expected is likely higher. For the maternal effect, we can see that for the first lactation, this ranged from 2 to 4%, but considering the first three lactations, this was equal to 19 and 25% using the linear and threshold models, respectively. And these likely suggest an overestimation of maternal heritability, as multiple lactations per cow were considered, and without fitting a permanent environment effect for that. We were unable to include the maternal permanent environment effect because only a small portion of the cows had recorded more than one lactation, more than one lactation recorded. And as a result, the model including the maternal permanent environment effect couldn't reach convergence. And how am I sure that it's overestimation? We tried like randomly hide all the repeated records for the cows that had this and keep just one observation. So we choose this randomly. And the results are very similar to this one that we found here for the first lactation. Because of this, I'm sure that is overestimated. For validation and model comparison, we have the linear regression of whole and partial EBVs, as I said before, where the intercept and bias give us idea about underestimation, under or overestimation, with the ideal value for both cases being 0. And our results actually were very close to 0, what is good. And the expected values for the slope and correlation are close to or equal to 1. For correlation, it was true. And for slope, it was true for almost all scenarios, except for the slope of the threshold model, considering the first lactation, where we had about twice the expected value, indicating that the EBV's values, in the partial data set were a little bit under dispersed in this case. Computing time for the linear model was at least 9 times shorter, as expected, because linear models are simpler than threshold ones and also has less parameters to be estimated. And regarding accuracies, well, these were better in the linear models, which was a small surprise to us because since threshold models are theoretically recommended for categorical traits, obviously these catch our attention and we decided to investigate a little bit more. And a good way to validate these results that linear models had performed a little bit better than threshold models was by comparing the detection power, in quotation marks here, of the model. So we took the bottom 5% and the top 5% of the bulls from each model. Bottom here is in red and top in blue. For the first 3 lactations and the first lactation. So you have both models. And we calculated the proportion of easy calves for that. So what we expected is how we calculate this. We took the 5% bottom, 5% top, and we saw from any calves how many of them was scored as 1. I mean, no problem during the birth. So just an example, let's assume we took just one single bull from the top and the bottom, both with 100 offspring. So what is expected is that the top bulls will have more easier calves than the bottom bulls. And how the model that detects great this difference is better. Because if the proportion were equal, this would mean that both the top and the bottom bull would have a similar proportion of easy calves, and the model is not like differing these two animals. In short, the greater the difference in proportion, which means the greater the difference between the red and the blue bars here, the greater is the power to detect difference between top and bottom bulls. And as we can see, this difference was indeed greater in the linear model than the threshold model. This means that there is a greater difference in the observed phenotype between top and bottom bulls when you use the linear model, which agrees with the results from the validation. And last but not least, we checked the rank of the animals in both models, threshold and linear, because if this correlation is high, it means that we would continue selecting the same animals regardless of the model. So the interesting about this part is that initially I only did the correlation between all the animals and then a correlation with the males with higher reliability. But then one of my reviewers pointed out that I should actually investigate these correlations for each breed and each sex. This is because of the Simpson's paradox. The Simpson paradox is where the association that appears in several separate groups of data can disappear or change when the groups are combined. So when I used all the animals together, this correlation was at least 0.9. But when I separate by breed and sex, we see here that regardless of sex for dairy breeds, the direct correlation were at least 0.89 for the direct effect, 0.87 for the direct effect and 0.89 for the maternal effect. But then when I look at the beef breeds, for the direct effect, this correlation remains high, 0.93. But for the maternal effect, it was very close to zero. At first, I was like, oh my gosh, what happened? But then I realized that it actually makes a lot of sense because if you remember the pedigree structure that I showed, we don't have any phenotype beef males. And because all the dens are dairy cows and the F1s are not phenotype, we don't have this measured for females in the beef side. But the good news for us is that here in the US, the beef and dairy is usually the final product, it'd be harvest. So the direct effect is the main objective. The maternal EBV in this case would be related to the calves of the beef and dairy progeny. But since we are not interested to meet these animals, it is okay to have such a low correlation. So what should you take home from my presentation today? Our results suggest that the data structure and pedigree, which are very particular to beef and dairy system, are unbalanced in terms of number of calves in each lactation, sometimes resulting in a change in the size breed method with specific cows. And in addition, the pedigree is shallow and unconnected. It makes estimating the variance components a challenge task. Furthermore, the high prevalence of scores equal to 1, 2, and 3 means that only the definition used for beef cattle in the US, where 1 is easy and 2 plus is difficult, is feasible. And based on these results, a kind of conservative, if I can say this, conclusion that I can make is initially only information from the first lactation should be used for calving evaluations in beef or dairy. And why? When we consider more than one lactation, we see that the maternal effect is overestimated because we couldn't account for the maternal permanent environment effect. And the maternal effect probably is capturing this effect. And possibly in the future, with a more robust data set and especially with a deep pedigree, it'd be possible to fit all the effects and have a better estimate using the first 2 lactations or even more lactations if people wish that. So I'd like to thank the University of Guelph and the Center for Genetic Improvement of Livestock Group for the invitation, especially Julia and Gabriela who contacted me. And of course, thank Peak Genetics, Ashley and John, who is in CDCB now, for trusting our work. Simone Guimarães, my advisor during my master and PhD at Federal University of Viçosa, and of course, all the professors, researchers, postdocs, students, and visitors from our lab at the Federal University of Georgia for all hard work. And with that, I'd be glad to answer any questions that you may have.
Thank you very much, Dr. Garcia, for your presentation. I would now like to open the floor to any questions, either from people here in the room or from those joining us online. Let me just, we do have a question here in the room.
Hi, Arielly. I have a couple questions, but I'll start with just one and I'll leave the floor open to other people. Did you have any repeated use of the beef sires in your data set across the different calves, or was it just once used in the cross?
I have repeated records for the bulls. In this case, let me show you the pedigree again. Yeah. Here. One thing that I think I don't mention is all the animals in this generation must have the information from the cows and bulls for be considered beef and dairy. So this amount of bulls generate this amount of offsprings.
Okay.
So yes, we used a lot the same bull in this case.
Okay, thank you.
Hi, thanks for the presentation. One of the questions I have is, about your conclusions is to use first lactation only. Now, just to clarify, when you say first lactation, this is the first calving, right?
Right.
Okay. Have you thought about looking at second and later, but not including first? I think you have first lactation and you have the first three lactations.
Yeah.
Or did you consider second and third as a separate trait? Because I think when farmers look at mating dairy cattle to beef bulls, they're going to try to avoid, they're going to give special consideration if they're going to breed a beef bull to a heifer. So they might choose matings very differently. So they'll choose a calving E sire, something that is not what they would normally do if they were looking for, more growth and better carcass traits. And so using second and third lactation animals, would that be more representative of what's going on in the industry?
Yes, at the beginning, we investigate the effect of the lactation. In this case, we consider the three lactations as different traits. So we run a multi-trait model, and what we saw is the genetic correlation between the three lactations is really high, more than 0.9. And because of this, we decided to join them.
Thank you. We have a question in the chat. I don't know if you're able, we can see that, but I can read that for you, in case you can't read. So she's saying, have you thought, a question from Isabel. She's saying, have you thought about the use of meta-founders or UPGS to improve the pedigree connectedness?
Yes, I thought about that, but for meta-founders, I think the most recommended in this case is use the genomic information, because I almost don't have pedigree information. So how combine these without genomic, right? So if I had the genomic information for these animals, I could think about the meta-founders, but without the genomic information is hard. And yeah, UPG is set as a default with the WF9, so we consider these, but because the pedigree is kind of not well structured, we still have a lot of hard time about this part. But thank you for the question.
Please, Flavio, go ahead.
Okay. Can you hear me, Arielly?
Yes, I can hear you, CGIL.
Thank you. Sorry. Thank you for your presentation. Really interesting work. I have a very quick questions just to make sure I understood. So in this very sparse pedigree that you had, you didn't use any phantom parents or genetic group strategy? No,
No.
was just what you had there.
Yes.
Okay. So the results that you presented for the heritabilities, for the linear model and the threshold model, you didn't express the heritability of the threshold model in the linear scale. You are
Yes.
showing there in two different scales, right? One and observed, the other one is the liability scale.
Yes.
That's what you presented, right?
Yeah, right. One is in liability and one in observed.
Yeah, but did you try to convert the liability scale to the observed scale?
Yes, I tried. But when I made it, I don't know why, I couldn't figure out why. The genetic effect was a kind of overestimated. It was like really higher than expected. So I couldn't figure out why it happened. But yeah, I tried the transformation in this case, but didn't work well. So I decided to present it in the.
But this is strange because when it's a binary trait, it's very simple to transform. And you had usually, I think, for all cases there, the underlying scale liability scale for the irritability was higher in the underlying scale. So you expect when you convert, because of incidence, to be lower. I was curious to know if it will be very similar to the linear model. It should be much similar if you convert.
Yeah. If I'm not wrong, for the first lactation worked well and the results were good, but for the first two lactations, it was weird. So we decided don't show. Yeah.
So, but this is related with my question. When you the link function that you use in your threshold model was a probit link function or a logit? Probit. Probit. Okay. Okay. Now that makes sense. Then being a probit link function, it should convert. No problem. Okay. So those are my questions, just to understand the results. Thanks a lot.
Thank you for your question.
So we have another question here in the chat. Is from Christopher. I really like this study lacking deep pedigree information, as I think this is an actual experience of most commercial sectors versus nucleus of seed stock or pedigree dairy production. Was a comment. And then, it can more. Let me see. As such, it gave insights on how one type of crossbreeding decision might affect an industry, and something to consider in robot milking of commercial cows were overtake formal data recording and pedigree string, for example. So, and he continues, or crossbreeding in general across other sectors, for example, sheep and breeding broadly. Was a comment from him. Thank you. I do have one question. Were you able to determine which cross of breeds performed the best for beef and dairy animals? And if so, do you know why? Do you have an idea why?
Yeah, I couldn't find difference between the breed combinations, but what I saw, the breeders, they have preference for some breeds. For example, they prefer Holstein instead of Jerseys and prefer Angus, for example, instead of the other breeds. And Simmental is well used too, but Charolais is really few. So I couldn't find, for example, difference between them, probably because of the unbalanced number of combination in these combinations. But yeah, you can see here the pedigree, they really like have a preference for Angus, probably because the birth weight for this breed is kind of lighter compared with the other two breeds.
I see. Thank you. Please, Flavio.
You're welcome.
Yeah.
I already hear that. I hear.
I forgot the question, really. So in your study, you calving ease was a trait of the calf,
Yes,
right?
in this case, yeah.
So have you thought about analyze your data as a trait of the cow, so that you would have the cow, and then the service sire would give you, the effect of service sire that will be the other breed.
So this is a good point because actually the calving can be considered a trait from the cow or the calf. In my case, it must be considered the calf because if I consider this as a cow trait, I don't have any connection between the cow and the bulls, the beef bulls. So at the end of the day, I will have just the breeding values for the dairy cows and for the dairy bulls. And the interest here is see the it comes for the beef side too. So because of this, we considered as a calf trait. So we could get
Yes.
the breeding values for the dairy and the beef side.
Yeah. Now in this case, because you don't, but if you had the genomic information, for instance, that would be a nice model to fit and compare, right?
It's true.
Like
I
how,
agree.
as a trait of the cow, and then have also as a trait of the calf. But yeah, in this case, just with the pedigree would not be possible.
Yes, it'd be really interesting if I had this information about genomic. And actually, I asked the company if it was possible. But what I understood is not like, as someone commented here, is not a seed stock group. So they didn't have the genotypes and they couldn't use these. But that would be nice.
Yeah, you had all the limitations of the data set, the commercial data set, right?
Yeah, for me,
But
it was really a challenge and really nice to work with this project because all the time I was thinking, oh my goodness, this is so complicated, it's so complex to understand the system itself, but it was really good. I love this project.
Yeah, great job. Thank you again, Daniela.
Thank you.
Thank you, Flavio. We have a question in the room.
Maybe first just a comment based on Flavio's comment there. Do you think it would be possible to fit a two-trait analysis treating the calving ease for the dairy dams when they're bred to a dairy sire versus a beef sire? So making it a cow trait, but comparing the beef sire, using it, treating it as a separate trait, maybe?
Okay, you mean treat as different or treat the den and side as effect? For example, because I tried a den side model, for example.
I was thinking more like treating them as separate traits. So treating calving ease to a dairy sire as one trait and calving ease to a beef sire as a separate trait.
No, this one I didn't try. What I tried was use a then and side model where we consider then and side as effect, and the results were not so good too. So we keep this one. But yeah, could be a really nice possibility. Thank for the comment.
I have another question that's more just a clarifying question. You said in your model that you fit the cow age as a fixed effect. And I was just wondering if you see age or parity having more of an effect on the dystocia rate. Like, do you see a big difference in dystocia in second lactation cows based on their age as well? Or is age just basically a way to represent the parity?
No, it was the age at the parent, the calf. That's the sorry. What is this? No, this 1 second. Yeah, here. Here you can see the difference depend of the age. So we have the first, second, and third lactation. So the prevalence actually was very similar, regardless of the age of the cow. But because the range was kind of big, we consider this as a coverage or try like to correct. Because the average for the first lactation, if I'm not wrong, 24 months, and for the first 3 is 30 something, I think. I don't remember from the top of my head, but the top of my head, but I think was this. Yeah, 39. Yeah, 24 for the first lactation and 39 for the second. So we decide to consider as a coverage because of this. The range is really high.
Okay. Thank you.
Thank you. We have a comment from Isabel on the chat. So she's saying if it's possible, one thing that you can try is to perform a simple PCA on your currently pedigree and see how the population structure looks like and assign phantom parents based on those clusters.
Yeah, should be a possibility. Thank you. Thank you for your comment.
Any other questions in person or
because
online?
what I saw like the main limitation that I would say about this analysis was the pedigree, because for example for beef side we have some bulls with a really high reliability, for example, but because they are not connected, we don't have the information about the relationship between them. It cannot contribute with the reliability of others. So yeah, we can have like extreme case. Some animals with really low reliability and some with really high reliability.
Okay. I see. So if no one else has questions, I'd like to end the meeting here. This has been a great discussion. Thank you again for presenting for us today, Dr. Garcia. I've learned a lot. And thank you everyone for coming. The recording will be posted on YouTube, and I will share more details about that with you later. So have you all a nice weekend. Bye.
Yeah, thank you all for the time, and I hope see you again.
Yeah,
Bye.
bye.
It's good in a way